Okay. Hey, everybody. Glad to see you all here. You guys can scoot in even a little bit more close. We can get a couple more people out of the way. Someone sent me an email and already asked for a couple questions to be done. So I've already got some problems lined up to do, but I wanted to see what else people had. So the ones that were asked about were 7, 8, 9, 13, and 14. Are there others we should look at besides those? And I'm pretty sure 14 is where the quiz stops for this one, right?
Can we look at 2?
Yeah, definitely.
And 5.
And 5. Any others? Right there. Okay. I think we've got time to do all those. So let's go ahead. Let's start with number 2. Who's got number 2 and what question that is? Because I don't know what question that is.
Just 1 second.
And also, funny thing for people that are in the hallway and feeling really too far away, someone in the last office hours, which was like 2 weeks ago, apparently was watching the live stream in the hallway. And they could like pop over and ask questions. I never thought of the live stream being watched like just around the corner. But
Okay. Number 2 is a 4-gram sample of a solid mixture is known to contain only sodium chloride and potassium chloride. The sample is dissolved in water and excess silver nitrate is added, resulting in the formation of a white precipitate. When the precipitate is filtered from the solution and dried, it weighs 8.5904 grams. And then, what's the precipitate? Write the balanced net ionic equation and calculate the percentage by mass of sodium chloride and potassium chloride in the original sample.
I'm so mean. So this question is not really a 129 question. It's a 127 question. And I got confused when you were first reading it because right now my 124 students are doing the carbonates lab. Do y'all remember the carbonates lab? So this was a lab you did in 127, and I'm all about bringing things back and remembering how we do things. This is a 127 problem. This is a problem from the carbonates lab that was considered a pretty tricky problem where we've got 2 reactions going on, right? So when we look at this, this is going to be, you're going to remember it once I start doing it, but you had a carbonate bicarbonate mixture and you had to add acid to it and it reacted some amount and then you're like, oh, what's the amount of carbonate and bicarbonate? And we had a couple strange things we had to deal with when we're doing that. So we've got Cl minus plus Ag plus goes to AgCl solid. And the problem is there's 2 sources of Cl minus. There's NaCl and there's KCl, both reacting with Ag plus. So now this means that in this reaction we have some unknown stuff and we have some known stuff. We know how much silver must have reacted because this reaction, the silver is in excess. And if the silver is in excess, we know how much chlorine must have reacted because there's excess silver, there's silver left over, but the chlorine is going to be used up. So essentially, we can use this mass of precipitate to figure out how much chlorine ion is in solution. And then we can use that to relate back to the amount of chlorine that must be in these 2. So we're going to get essentially 2 equations that we have to deal with. We're going to have one equation that's going to look like this. We're going to have something that's like moles of Cl minus is going to be equal to the moles of Cl minus, well, we can even do it like this. The moles of NaCl plus the moles of KCl. And we can do this in a one-to-one way like this, where I don't have any mole ratios or anything, because it's all a one-to-one reaction, which makes it actually easier than the 127 problem that you don't remember. So, yeah, she needs to get into this drawer, I think. Sorry about this, Linda. They have lots of questions. So, this becomes our first equation, and we can figure this out. We can figure out the moles of Cl minus from the precipitate. And then we have a second equation which we can figure out the amount of NaCl and KCl from the solid. So if we have 4 grams solid, we know that's going to be X grams of KCl plus Y grams NaCl. And so what we end up with here is 2 equations with 2 unknowns. Is this seeming familiar at all? Couple nods yes, couple nods no. Okay. So just imagine if instead of Cl minus I had HCl, and instead of these I had sodium carbonate, sodium bicarbonate. Then it's the same problem we did all the way back in 127, which for some of you might have been over a year ago. So, but notice the reason the reason I said this is mean is because this problem is actually not very related to any of the things that we've been doing this quarter, right? It's a precipitate problem, and you can look at it as a qualitative analysis precipitate problem because we're trying to figure out what's in the unknown powder. So in those ways, it kind of relates to lab, but it really is just a tricky stoichiometry problem that takes a lot of chemistry thinking. And in that way, I like to bring it back and kind of hopefully jog those memories of things from the past, which has really been the entire theme of Chem 129, right? Everything we've done, we really have not done much new stuff. We've just done old things in different context. So, I'm going to go ahead and, what's the question actually asked for at the end there? Yeah, we've got problem 2 right here. What is the precipitate balance? I calculate percentage by mass. So I put X grams and Y grams here because I know I want percentage by mass. So I'm going to calculate my moles of NaCl and my moles of KCl in terms of my grams, right? So I'm going to have X grams. What's the molecular weight of KCl? And my Y grams. So I'm going to replace my moles of NaCl with my grams divided by its molecular weight, which I don't know off the top of my head. 23 and 35 is 58.
It's 74.5 for potassium chloride.
74.5. And this one I think is 58.
Yeah.
Cool. So when we look at this, we can kind of see I can get rid of my moles of NaCl. Notice though the units of this, Y divided by 58, because this is grams per mole NaCl, and this is grams per mole KCl. My units still work out, where X divided by 74.5 is still my moles of KCl. My Y divided by 58 is still my moles of NaCl. And now I essentially have 2 equations to, oh, and then I need my moles of Cl minus. This is going to be 8.5904 times 1 over the molecular weight of silver chloride. 35 plus something big. I can't remember silver off the top of my head.
$143.3.
143.3. Right, and this is going to get, and then we could also, if we want it to be really chemically correct, we have our 1-to-1 mole ratio of 1 Cl minus per every mole of AgCl. And then I can plug that in there. And now what I've got, 8.5904 divided by 143.3, I've got 2 equations, 2 unknowns, substitute and solve. Sound familiar? Still some yeses, still some yeses. So, like I said, this problem 2 here, does not have a lot to do with the things we've been doing this quarter, but it's something that we should be able to do because we all passed 127.
So would something like this be on the quiz/finals?
If it's on the homework, it's a valid question.
Sorry.
So that's problem 2. Are we ready to move on? Did anyone get an answer to this that they're willing to share? What'd you get? So once you get x and y, you're going to do x divided by 8.5, y divided by 8.5.
I got 57.5% KCl and 42.5% NaCl.
I'm going to put a question mark because I'm not checking that. I'm just believing somebody's work. I would want to do it myself to make sure that that's correct, but at least one person got that answer. Did anyone else get that answer?
I got that too, but I divided it by the 4 grams, not the 8.
Oh. Yeah, it should be divided by the 4 grams. I misspoke.
Okay,
Yeah.
I got the same.
4 grams, because it's the unknown we want to analyze, not the precipitate. Yeah. Should be divided by 4. I misspoke. So, 2 people got this answer. Of course, on the quizzes, you have to show your work. So if you just like memorize this and write it down, you're not going to get credit. Got to show your work. Are we ready to move on? Okay. No one said no. No one said yes. So I'm going to go with my answer and just move on. Problem 5. Anyone got problem 5 handy?
In the
Someone else.
presence of excess ammonia, NH3, quantitatively describe how much free, uncomplexed, and nickel 2+ ion will remain in solution at equilibrium. Explain.
So this is a bit of a kind of beginning thoughts of how we think about metal complexes, right? When we look at this, we really want to say, I don't have numbers for anything. How the heck am I supposed to think about this? What's one of the things we know about KF?
It's usually really big.
In general, KF is usually much, much bigger than 1. Right? KFs that we've seen are on the order of 3 times 10 to the 8, 5 times 10 to the 15, 6 times 10 to the 21, right? These are usually enormous numbers. What does an enormous number tell us? I'm going to even be so bold as to say all. We know it's not really all. That's why I'm putting it in quotes. When we've got a number that big, we're really going towards all products. So if I've got excess NH3, how much nickel is going to be left in solution?
None.
Our concentration of nickel 2+ is going to be approximately 0. Now, we could be a little bit more detailed in this, right? If we thought about the reverse reaction to excess NH3, well then, if we wanted to get to numerical values that depend on how much excess NH3 there is, you could also say this is going to be the other thing. If we wanted to do something more specific, we could say on the order of 1 over KF, right? Because this reaction is going to be really product favored, so the amount of nickel left in solution is going to depend on the reverse. And with the excess NH3, just saying we've got tons left over, I'm going to do my NH3 divided by, or my KF, ooh, I got to think about this now. I'm going to have something that's going to be like nickel 2+ NH3. You don't have to do this much. If you get this, you're good. This is the answer I was looking for. But we could always push our thinking a little bit further, right? We're going to have like NH3 to the 6 is equal to KF. If we've got excess NH3, we're going to say that, wait, now I got to think about this. So we want to do the reverse of this. So I'm going to do, I got to think about this now. Nickel 2+ plus 6 NH3 goes to nickel NH3 6. I just happen to know that it's NH3 6. I would have to tell you that in the problem. 2 plus. And then we want to look at the reverse because we're going to form all that. And this is going to go to 0. Then I want to think about the reverse, so I'd have to do the reverse of this. I would want to look at K reverse is equal to, oh, and I forgot one more thing, liar. Because it's not just a KSP, it's products over that's where I messed up. Okay, so I knew I did something wrong as soon as I wrote that KF down. I was thinking too much of my old precipitation problems. If I look at this and I'm going to do products over reactants, my KF is going to be equal to the products. That's going to be the nickel complex on top, not the reactants, of course. 2 plus divided by my nickel 2 plus and my NH3 to the 6. Now if I reverse this, I'm going to have my K reverse times, I'm going to have 1 over KF times my NH3 if I did the reverse. And again, this is going further, but this is how, if we wanted to get to a mathematical solution, which I think either problem 6 or 7 actually has us do this. So this isn't completely pointless right now. The reverse reaction would be our nickel NH3 6 2 plus complex falling apart to 6 NH3 plus nickel 2 plus. I would have my 1 over KF equal to nickel 2 plus NH3 to the 6th nickel NH3 to the 6th 2 plus, like that. These things are going to get multiplied over 1 over KF, and assuming that the excess NH3 isn't like extremely excess, we can say that the concentration of nickel ions and the concentration of NH3 ions are probably going to be on the same order, right? We would need specific numbers to really do it, but the point is if these things are like on the same order, we're pretty much going to get the nickel is proportional to 1 over KF. That's a lot of approximations. But really, since the KF is a huge number, we know that the nickel concentration is going to tend towards 0, tends towards a concentration of like 10 to the minus 15, 10 to the minus 18, 10 to the minus 20. All of it's just a thought experiment, right? And one of the big problems, I'm going to go ahead, one of the big problems people have with this type of work, like doing these calculations, is they get caught up so much in doing the math that they forget to think about the problem before they start doing the math, and they start running down the wrong path. So it's really important to actually think and just have this concept of, oh, I expect my nickel concentration to be close to 0 before we start doing the math. So that way, if you do a problem, and I think it's 6 or 7, when you do the problem and you get a nickel concentration close to 0, you're not surprised. Or if you get a nickel concentration that's like close to 1, you go, I made a mistake, right? Having that thought beforehand so you don't believe nonsense is important. Are we ready to move on? Sorry, I got so sidetracked. Yeah?
When you actually do the calculations, do you just assume that the nickel at equilibrium to find like the concentration of your, like for the formation?
We would have to be given numbers, right? We can't do this without numbers.
So like if you're doing like the ice table, I guess, would you just at equilibrium you just set nickel be 0, whatever subtracted from your excess of your
Exactly.
To find the concentration of your
to find the concentrations we'd start here. Yes, exactly. Okay, so that was problem 5. Great. Problem 7. Who's brave enough to read out loud?
Write a balanced net ionic equation for each of the following dissolution reactions and use the appropriate KSP and KF values to calculate the equilibrium constants for each.
Okay.
And the first one is AgI and aqueous NaCN to form AgCN2 minus.
How many are there on this?
3.
3? Should we just do the first? So let me get a quick poll. 1, 2, or 3, which one do you want to see? Most people seem okay with 1. Okay, so we'll go ahead and do 1. So this is recognizing the fact, gosh, this goes back to homework like number 1. Or maybe it was homework 2. Do you remember when I had you write down the 2 chemical equations to show how acids and bases affected the solubility of different solids? This is the same thing, except for instead of acids and bases, we're now doing formations. Right? So when we look at this, we say, okay, clearly I've got 2 chemical reactions, 2 competing equilibria here. I've got my AgI solid that's going to disassociate into Ag plus I minus. That's one thing that's going to happen. That's going to have a KSP associated with it. I am also, and this is problem 7, okay. I also am going to have this Ag plus. Remember when we were doing this with acids and bases, we were looking at the anion. We can now do this with the cation and say, I've got Ag plus 2Cn minus. That's going to have some equilibrium to form the AgCN2 minus. What's the name of this? Say it in your head at least. Arginate, yes. Dicyanoarginate. And we got the ATE ending on our argentum, on our silver because of the minus, so it's dicyanoarginate. Typically with silver, and this is kind of weird, to be completely 100% IUPAC, like International Standard for Naming Corrected, would be dicyanoarginate parenthesis 1, right? Because that's the charge on the transition metal. Chemists, however, almost always leave off the parenthesis 1 when it's silver, because silver really only has the 1 oxidation state. Silver plus 1 is pretty much the only silver oxidation state you ever see. So that should be there. But we've got this second equilibrium. This is going to have a KF associated with it. Right? So we've got the equilibrium of the iodine interacting with the silver versus the equilibrium of the cyanide interacting with the silver. And to figure out which one wins, we put these 2 equations together. You can see my balancing is 2 plus there, add an I minus there. And when I put these 2 equations together, do I need to flip a reaction or change the direction of a reaction in order to get my equation in green? Just nod yes or no. No, I don't. Right? That means when I put these together, my K reaction, or if you want to call it K overall, or if you want to call it K total, all of those things are really communicating the same thing, right? I'm looking at this reaction. Since I did it in multiple steps, I can think about it in terms of the overall reaction. Since I did it in multiple steps, I can think about it in the total. All 3 of these things are trying to communicate the same thing. I know that's a little frustrating. They're all just equilibrium constants. This is going to be KSP times KF. So in order to finish this problem, we'd have to look up the KSP for AgI and the KF for the dicyanoarginate. And then we just multiply them together. Question?
So when would you have to so if you had to flip them like if it was on the other side,
right?
1 over KF or 1 over both of them and then multiply them?
Yeah.
Okay.
So if the reaction was completely flipped, that would be the case. If we were dealing the places where we saw this is when we were doing weak acid, weak base, we usually flipped one of them. That's why we had Ka of the first thing divided by Ka of the second thing. If we had a Kf versus a Kf, one of those is going to be flipped, so we'd have a Kf forward versus a Kf reverse, so you'd have a 1 over Kf there.
But for these, you'd do like you'd never have like KSP divided by KF. It'd always be like 1/KSP times 1/KF.
Yeah, because of the definition of how we write KSP, it always turns out that the KSP is going to essentially be in a forward direction when we're thinking about it. And since most of the time when we're adding something to form a metal complex, we're doing it to dissolve a solid, it almost always ends up being just KSP times KF. And that's just because of the ways that, because of the questions that are interesting to ask. We almost always end up with it going that way. Number 8. Any other questions on this problem? Okay, number 8. And then B and C are essentially the exact same thing, right? You're just going to be doing this again for different, precipitate different complex. But it really is very similar to the problems we were doing back on homework 2. Same idea of how does this affect it, except for we're now at the point where we can actually calculate how much it affects it, not just if it does or doesn't, but how much it affects it. Number 8.
What is the molar solubility of AgI? Then part B is in pure water, B is in water with pH of 3, C is in a 0.5 molar NaI solution, and D is in 600 milliliters of a 0.91 molar NaCN solution.
Great. So this is a glorious, glorious problem. This is another problem that should look really familiar, right? Back on homework, again, homework 1 or homework 2. We looked at the solubility of silver iodide in pure water. That's like the first problem we did in this class, right? You should be able to look at this and just instantly be like, square root KSP. Does that sound familiar to everybody? Right? We could set up the ice table. We're going to get our x squared. Square root of KSP is going to give us that. For problem C, it's going to be common ion effect. You know, you've got the iodide there, so that's going to change it. So instead of just being square root, it's going to be like KSP divided by 0.5. Right? Again, relatively easy, relatively straightforward. B is a little bit tricky. And then D is the actual problem that's new. But essentially, this problem is bringing back all of that stuff we've done before. You notice we've got solubility, we've got competing, we've got common ion effect, we've got pH effects, and now we've also got metal complex effects. This problem essentially covers almost the entire quarter. It's great. Does pH affect this problem? Okay, let's think about this. If we had silver iodide, would that, going back to the same problem we just did almost, would silver iodide have its solubility impacted by a decrease in pH? How do we tell? What's the magic phrase we use? What's the thing we look for that tells us?
It forms like strong.
Does it form a strong acid or a weak acid? When I take my H plus and I interact it with my anion, does that anion form a strong acid or a weak acid?
Strong.
Strong acid. So is the pH going to affect the solubility? No. Problem B, the answer is the same as A. You actually don't have to do any math for problem B. I always have a few students that run away with this problem. They write down, okay, I calculate my H plus concentration, I do my reaction of H plus with I minus. They're like, oh, I don't have a Ka for that. What if I do something with Ag and H plus? And they start doing all this math and all this calculations. But this is not a calculation problem. This is a conceptual problem. The answer to part B is pH does not impact the solubility of AgI because HI is a strong acid. Question.
If it made a weak acid instead, it could affect it.
Yes. So, and this goes back all the way back to the first midterm. We could have done this problem instead of for AgI, we could have done it for AgC2O4, silver oxalate. And then we would have had to say, okay, what's the equilibrium of the silver iodide KSP versus the Ka of the silver oxalate? And we would again come up with a K overall, and we could see that kind of calculation. The mathematics are a little bit heavier, but we're at a point where we can almost do that. And that's pretty much what we're going to do with problem D. Except for instead of it being a weak acid equilibrium, it's going to be a metal complex equilibrium. So yeah, we definitely could do that. But that, in this problem, not the case. So then the question becomes, how do we do part D? If you notice, this is almost exactly the same problem that we did in problem 7, right? I've got AgI, I've got NaCN. This is going to be AgI plus 2 NaCN goes to AgCN2 minus plus 9 minus. We can get rid of the sodium there so our charges match up better, right? Sodium spectator on doesn't matter. Now I've got 2 minuses, I've got 2 negatives, that makes me much happier. My K overall is going to be equal to KSP times KF. Just like the problem we did before, I could think about splitting this up into the precipitate equilibrium and into the metal complex equilibrium, but we just did a problem like that, so I'm going to jump that and say it's just these two times each other. If I remember correctly, because I did this problem yesterday with a student that came in, this is on the order of 3 times 10 to the positive 4. Does anyone have, and that is, I might be remembering the wrong problem, but you look up the KSP for AgI, you look up the KF for AgCN2 for that dicyanoarginate, and you get something that's on the order of 3 times 10 to the positive 4. Does anyone have that number handy? Am I close? Am I totally off? No one knows. Okay, I don't know either. I'm pretty sure it's something that's a large positive number though. So something that suggests we have 3,000 times more products than reactants. Sorry, 30,000 times more products than reactants. So in this case, how much silver iodide is going to dissolve? If I've got a large K reaction. All of it, depending on what, all of it relative to the limiting reactant. So if my sodium cyanide, so in this case we can imagine I've got a bucket of 600 milliliters of 0.19 molar sodium cyanide, and I'm tapping in as much silver iodide as I can until I see some that doesn't dissolve. So essentially my AgI is going to be excess, or I'm going to be looking for the point where my AgI is equal molar to my CN minus. So that means this number of moles, 600 times 0.91 times the mole ratio of 1 to 2, that will be my amount of AgI that dissolves. That's it, right? After we go through the thinking and recognize that we've got a large KF, or sorry, a K overall or K reaction, then I can look, and say, this problem is actually just stoichiometry. And then I could calculate it. Now, the way that this problem is worded, you can stop there and just say, it's going to be an equal molar amount to the sodium cyanide, because the redissolve amount, or actually in this case, the reprecipitate amount is going to be small. It's going to be on the order of 10 to the minus 3, right? So you can kind of get away with just saying, approximately 0. Now, that's because the question doesn't ask about, or not approximately 0, it's going to be approximately this amount plus something that's small, right? X is small approximation. The place where this would be more interesting is if instead of just saying how much AgI dissolves, if I also asked, and how much CN minus is left in solution, then you have to do the ice table as well. right? Because you can't say approximately 0 for that because it's 0 plus a small number. So if on this problem I had and how much Cn minus is left in solution, then you'd have to do the ice table. But with the way this problem is worded and what it's asking for, you pretty much can just say it's the equal molar amount because you've got a large K overall. And I'm not going to do the and calculation because I think that's problem 9. I think we're about to do a calculation like that. Any questions on this? Again, notice in this whole problem, it's almost all conceptual work, right? I didn't do much math at all. It was all, how am I thinking about the problem? How am I putting my concepts together? I know everyone loves to churn through the calculator, punch in the numbers, and get values and be like, yes, that's my answer. But a lot of what we're getting to now is just conceptually, how do we think about it? How do we we've got so many things we've gone over this quarter that are all slight variations of the same thing. How do we put that together and think about it the right way, the way that makes chemical sense? So, ready to move on? What is problem 9? Someone else who hasn't read yet.
Silver ion reacts with cyanide ion to form a colorless complex ion, silver cyanide, or argent cyanide, which has a formation constant Kf equals 3.0 times 10 to the 2. Calculate the concentration of Ag plus in a solution prepared by mixing equal volumes of 2.0 times 10 to the negative 3 molar arginite nitrate and 0.200 molar sodium cyanide.
Exactly the problem I just said I wasn't going to do. But here we are, we're doing it. Right, so this one specifically asks, what's the amount of silver left in the solution? Now this one's a little bit easier, right, because we're not looking at competing equilibria, we're just doing a straight equilibria. But we still have this situation where one is limiting one's excess, and that's going to give rise to having to do the forward reaction and then the reverse reaction. This is almost exactly like the solubility problems we did back on homework 2, right? Kind of still stuck in the same route we've been in all quarter. Reaction, equilibrium, reaction, equilibrium, reaction, equilibrium, reaction, equilibrium. So reaction equilibrium. Now, since I've got a very large equilibrium constant, Kf is 3 times 10 to the positive 20, I can assume that this is going to go to completion, so I'm going to go ahead and do a stoichiometry table. But I need these molarities in moles, so what volume do I have? It doesn't say. Right, it just says equal volumes. So I could, if I wanted to keep this as generic as possible, I could do times V times V. My V's will eventually cancel out because it's the same volume. But I find it easier just to pick an equal volume. What's a good volume to pick?
1 liter.
1 liter. $1. Right? That makes the math much easier. I'm going to have minus 0.002 minus 0.002 times 2 to 1. Sorry, got it carried away. Start reaction excess. I'm going to have 0 left over because my silver is my limiting reactant. I'm going to have, math in my head, 0.196 moles left over. And I'm also going to have plus 0.002 and 0.002 moles produced. That's my Kf. Then I can go ahead and set up the thing. You guys know how to do reverse reactions, right? Yeah, okay, let's go ahead and do it. So then we set up the reverse reaction. Ag Cn2 minus is going to go to Ag plus Cn minus. Don't forget your 2 there. Notice if we just had the stoichiometry, we'd be like, 0. But 0 plus a small number is not 0. We can't just access small it like I said we could on the last one. We actually have to do the ice table here. My K reverse is going to be like 3 times 10 to the minus 21. It's going to be like 3.33333 because it's 1/3 times 10 to the minus 21. Close enough. I'm going to have 0.002 divided by 2 liters. I'm going to have 0. I'm going to have 0.196 divided by 2 liters because I added those volumes together, right? I added 1 to 1. So this is going to be 0.1. 196 is going to be 0.98. 0.9. Whoa, that doesn't make sense. Someone fix my math, please. 0.098. Thank you. 0.098. 0.1. I'm going to have minus x plus x plus x. This is going to give me 3 times 10 to the minus 21 is equal to products over reactants. This is approximately 0.098. This is x. This is approximately 0.1. I'm going to have x times 0.098 divided by 0.1. What'd I forget? Squared. Remember, we've been dealing with acids and bases and everything having 1-to-1 ratios so often that it becomes really easy to forget we need those molar coefficients. Don't forget your molar, and technically this should be plus 2x, right? Don't forget your molar coefficients. They exist still, we just haven't had to think about them for a while. Solve for x, that's going to be my amount of silver left in solution. And notice, I set up this problem a particular way. This problem was specifically set up so the silver would be the limiting reactant and you would have to do the ice table in order to find the silver concentration. If I asked what the cyanide concentration was at the end of the reaction, once the reaction reaches equilibrium, you'd be done as soon as you did the stoichiometry because you're just going to X is small anyway. I set up this problem so you had to do the ice table. Cool. But notice, did I do anything new or strange? Does it feel like we're still back in the second week of class? It's timeless. This class is timeless. That was problem 9. We ready? Yeah, question. Point 1. Oh, good grief. That should not be 0.1 at all. That should be 0.001. Blarg. So, thank you for that. I got carried away with my sig figs and just made a huge typo. I divided wrong is the answer. Yeah, that was a mistake. 0.002 divided by 2 is not 0.1. It's 0.001. So make sure you get that correction in there. Yeah.
And you were saying if you were trying to see how much cyanide was left in solution after the reaction, you just do 0.196 divided by the total volume.
Yeah, right. Because if we look at our ice table, since we're using the X is small approximation, I don't actually need to do the ice table to get that since I can use the X is small approximation. Other questions about this before we move on? Okay. Problem 12. I don't know what it is.
Yeah. Give the coordination number, ligand number, most likely ligand geometry, and oxidation state of the transition metal in each of the following coordination complexes.
Okay. How many problems are there?
A through J.
A through J.
So it's like 9.
Let's pick 2 of them. Everyone look at the list if you got it handy. Pick your favorite 2. or your least favorite too, as the case may be.
Do we have to know what EDTA is?
That's the one I said was the, I knew there was a polydentate on the homework that I don't ask you to remember. That's the ethylene diamine tetraacetate. So that is a tetradentate. That does 4 covalent bonds from one ligand.
Could we do J?
Yeah, what is it?
It's got PT, EN2, BR2 in brackets. So that's the complex aspect. And
Oh, really?
CLO42 on the back.
Cool. You know what should be added to this problem? Also name it.
It is.
Oh,
on
name
there.
is on there too?
That's part 13 is name that thing.
Oh, okay.
So I just don't remember what the actual metal name is, so I didn't.
Platinum.
Oh, thanks. So easy.
So this is diabromo bisethylene diamine, platinum 4 perchlorate. Dibromo. Now, ethylene diamine, since it has the di in there, I can't say diethylene diamine, and it'll sound like it's 4 things. So I use the bis. And I don't change the end of platinum because this is the cation. Platinum 4. And I figured out it was +4. Ethylene diamine is a neutral ligand. Bromine's a -1 ligand. Perchlorate is a -1 anion. So that's -1, -2, -3, -4. Platinum has to be +4 to balance that out.
So the rules when you're naming metal complex cation is that you start with the ligands in alphabetical order.
Yes, ligands in alphabetical order. And at this point, I don't need to say diperchlorate, right? When I'm doing an ionic connection, I don't put the prefix because the charge tells me how many there are. That would be redundant information.
Kind of implied then.
Yeah, the number of perchlorates is implied. But how can you not love these names? I mean, look at this. Where else do you get to write words like that? Where that's the word. It's all one word. It's just silly. I love it.
Why is it 4?
I feel like this would be a winning word in Scrabble.
Why is it 4?
So I don't think it would fit either. Cover the. So if someone did like platinum first, and then you could do like ethylene diamine, and you'd be like, no, this is a metal complex. It's real. But it's a name. Names aren't allowed in Scrabble. Darn it. So why is it 4? Sorry, I was getting carried away there. So we know that the perchlorate's a -1 anion, or hopefully you remember that. That's again a 127 thing. I told you the first day of class I expect you to remember all of your common ions. So we know that chlorine's a the perchlorate's a -1. We also know that the bromine's a -1 when it's a ligand. So I've got 2 -1s there, 2 -1s there, and the overall charge is 0. So I have to have some charge on platinum that makes it so this is overall equal to 0. Has to be +4. So +4 -2 -2 is 0.
Yeah. When would we use the 8 ending again?
So if the metal complex was the anion, so if the metal complex, notice overall this metal complex has a +2 charge on it. So since it's a cation, we use the platinum. If it was an anion, do we have an example from number 12 where we've got an anion?
Yes.
What's that one? Oh, sorry. Ligand number is, let's finish this problem before we move on, but like we'll do, what is it? We'll write it down for now.
All right. It's 3 ammoniums as the cation, and then the anion in brackets is RHCl6.
Yeah, I gave you a rhodium complex.
It's 3 NH43.
That's going to be weird to say, but we'll get to that in a minute. Before we get to that, let's actually answer the rest of the problem. So we are doing 12 and 13 at the same time right now, right? Because that's the answer to number 13. Number 12, the coordination number is going to be 1, 2, 3, 4, 5, 6. Remember, ethylene diamine's a bidentate. So the coordination number in this case is 6. The ligand number is 1, 2, 3, 4. So the reason that the coordination number and the ligand number don't match is because we've got a bidentate in there, right? We've got something that can form multiple covalent bonds, a chelate. The likely geometry of having a coordination number of 6 is?
Oh, I just have a question. How do you get the ligand number? Sorry.
The ligand number is just the number of things.
Okay.
So 2 ethylene diamines, 2 bromines.
Okay.
But then the coordination number is the number of covalent bonds. So this forms 1 covalent bond and 1 covalent bond. These form 2 covalent bonds each. If we've got a coordination number of 6, the geometry is? Oxidation number we figured out already, +4. We did that to name it. We talked about how we did that. So that's that one. So let's go ahead and name this thing now. This is ammonium. Not ammonia, we need the ammonium, positive anion, right? Ammonium, and if I remember correctly, this is, I don't need to remember correctly yet, then I'm going to have a space, I'm going to have hexachloro, that's the system, right? Hexachloro, yeah, rhodium is the element there. But I'm going to take the ending and change it to ATE since the metal complex is the anion this time. Now, to figure out what Roman numeral I put in there, that is to say to figure out the oxidation state, we're going to do the same thing. Chlorine is a -1, and I've got 6 of them. NH4 is a +1, and I've got 3 of them, and this thing is going to be overall 0. What does the rhodium have to be?
3.
+3. So I'm going to go ahead and toss in Roman numeral 3 there. Ammonium hexachlororhodiate 3.
So
Yes.
you don't have to say like tri-ammonium.
Right, and again here, when we've got the ionic bond, we put the space, and we don't need to put triammonium because the charge on the rhodiate implies the fact that there's going to be 3 ammoniums. Right? So if we said triammonium, we'd be putting redundant information. So coordination number in this case is 6. Ligand number is also 6 because I've got 6 monodentates. My geometry, since my coordination number 6 is octahedral, my oxidation state's +3. That takes care of 12 and 13. A whole lot of naming, a whole lot of definitional work there. One more problem on our list. Oh, question.
So with like, when you use like ferrite and arginate, is that only with silver and iron when they're anions?
Yeah, that's only silver and iron when they're anions. Technically, we could use their Latin names even when they are non-ionic, like when they're not anionic. We could say, you know, oh, now I gotta remember Latin. You know, ferrous and ferric and ferrate are all different charges on iron. I would have to look it up to remember it now, but you would use the Latin name. I can't remember them off the top of my head. I can't remember the correct suffix.
Okay, so but
Yeah, so I only use them when they're anionic.
okay.
And now I want to look it up. Later, after office hours. Are there any other questions about this before we move on? Any other in the A through J that you're like, no, I really want to see this one? Ferrum.
For one of them, it says EDTA inside the parentheses.
That's one of the polydentates that you don't have to memorize, but I put it on the homework just to be like, hey, there are other polydentates, there are other ligands than besides, like, we're learning some core, like the most common ligands, but there's a whole lot of other things that can, act as ligands with metal complexes.
So how do you name that?
So that EDTA is ethylene diamine tetraacetate, and I think there's only one of those, right?
Yeah.
So you just have to put that ligand name on there, all one word. Ethylene diamine tetraacetate. On to number 14. Okay. What does number 14 ask us to do?
Write the formula of each following coordination compound.
Oh, so this is just the backwards of what we just did, right? Is there a good one there we should do? I'm going to have to look at that. You can just read a name and I'll do it as you read it.
Triamine, trithiocyanator, rhodium.
You said rhodium?
Oh, yeah,
And it's rhodium 3?
Yeah.
There you go. Thiocyanate. Is there another one anyone wants to read? Notice the thing I love about these names, it is just a grocery list of what's in the complex. It really is. It's just like carton of eggs, gallon of milk. List is all out. Okay. Someone else wants to read one? So it's just that kind of.
When it comes to the ligands, when you're right, it doesn't really matter what order they're in.
Technically, no. Right? There's no rule for the order in which you write the ligands. Some people like to put them in alphabetical order just because that's the way you name it. Some people like to think about the reactivity and the complexing and which ones are going to be harder to react off of the metal center, which ones aren't. But like, it's really, you can put them in whichever order best represents the chemical reaction you're about to do. Right? So if I was going to do something that was going to react with the ammonium, I might want to put the ammonium further out. If I'm going to do a reaction that's about to react with the thiocyanate, I might want to put that one out. And then there's also the possibility of also doing it this way. Right, so thiocyanate is one of our linkage isomers, and it can attach in the SCN way or in the NCS way. And when it attaches in the NCS way, they put another special like prefix or suffix on it.
I mean, does that also apply for like cis and trans because they can be?
Yeah, so we could call this. We could put an extra thing on each of these names for the isomers, and we could call it we could say this is I want the cis version or the trans version. But with our general naming, I don't think I've got many good questions on the homework for the isomers. I need to add some homework problems for that.
I have one more to write out.
Sure.
Yeah, sodium hexacyanoferrate 3.
Oh.
Okay.
Do y'all remember this compound? Chem 128? The corrosions lab where you made Jello?
Oh, yeah.
Every time I bring something up from past class, you're like, no, we never did that. I'm like, you had to. That definitely happened. You had the nail in the jello that was like yellowish and then it turned blue or pink. The material that turned it yellow and became blue was sodium hexacyanoferrate. This was the compound. Because when this compound interacts with oxygen, this compound becomes blue. And as it is, it has this kind of yellowish red color. So this is actually a detector that you've actually, a chemical detector you've used before.
So the 3 at the end indicates that there's 3 sodiums?
Yes, because the 3, well, what the 3 at the end really indicates is the fact that the iron is +3. And I've got 6 cyanides, so I know that this thing is overall -3. Right? Actually, let's change that a little bit differently. The Roman numeral 3 tells us that's a +3. I know that this is a -1 times 6, because the cyanide's a -1. And then from that, I can figure out that this is going to be overall -3. Then I need 3 sodiums to balance it out. Yeah.
Can you do the coordination number and Ligand number and explain it?
Let's do both of those on this. So that is a definitional problem, right? We want to define what is the coordination number. What is it? Number of covalent bonds, right? So when I look at this, the number of covalent bonds between ligands and the metal center, right? I'm not going to count the bonds in the metal. I'm not going to count these nitrogen-hydrogen bonds. I just care about the nitrogen to rhodium bond. So when I look at this, I'm going to have 3 covalent bonds because the ammonia can only do 1 covalent bond each. So that's 1, 2, 3. The thiocyanate can do 3, 1, 2, 3. So that's going to be a coordination number of 6. If I look here, I've got 6 CNs. That's also going to be a coordination number of 6. Now, ligand number is not the number of covalent bonds. It's the number of ligands that are giving those covalent bonds. In these 2 cases that we're looking at, since all we have is monodentates, that is to say every ligand only gives 1 covalent bond, the number of ligands is the number of covalent bonds. So in this case, my ligand number is also 6, my ligand number also 6. This one, it's really easy to see that the ligand number is 6 because I've got 6 cyanides. This one, we have to say I've got 3 ammonia ligands and I've got 3 thiocyanate ligands, so that's going to be 3 plus 3, 6 ligands. Yeah?
But the numbers are different when the ligand is a bidentate.
Yeah. So if we go back to aura, anything that's not monodentate, anything that's a chelate, right? So whether it's a bidentate, tridentate, or a polydentate. So if we go back to the ethylene diamine tetraacetate, the EDTA, that's going to be 1 ligand with a coordination number 4 because it can form 4 covalent bonds.
So like, why is the ligand number 6? If I'm confused, because the iron and the thiocyanate. No, sorry, the one right below.
Cyanides, yeah.
Yeah. So why is it we've got 6 of those and 1 iron?
Right.
How does that work?
So, how many things are ligands?
Isn't it just everything that's attached to the central, or everything that's attached to the iron?
Yeah. How many things are
So
attached to the iron?
6. 6. So where's the sodium attached?
The sodium is an ionic bond that's outside.
Oh.
It's not a covalent bond.
So
That's part of why we use this weird new bracket notation for our metal complexes. So the ionic bonds don't matter. So if I were to draw this compound trying to represent this, I'd have my Fe, I'd have my, I'm going to draw this in a little bit of a weird way, right? Because it's the nitrogen that's going to be providing the lone pair to right? So this whole thing has a -3 charge. And then I'd have just like a sodium here, a sodium here, and a sodium here. Right?
Okay.
Covalently, not covalent bond, ionically bonding. just
So
through the Coulomb force.
Everything inside the brackets is covalently bonded.
Yes.
Okay. Got it.
So we're supposed to have 3 bidentates memorized, and then if
2.
2, and then if not, you'll tell us.
What are the 2 bidentates?
Oxalate and ethylene diamine.
Can we write EN for that?
Yes. 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 As long as you define EN as ethylene diamine. And there are some situations, if I ask you to draw a structure, where it won't be helpful to do that, right? Because if I just draw EN here, then I have to like draw bridging across. So like when you're trying to identify isomers, just having it written as EN is not always that helpful. But you're welcome to do that as long as you know what you're doing and you make sure that I know you know what you're doing. Any other super pressing questions? I might go ahead and stop the video, and then if there are other questions, we can go back and do some of these other problems as well. If people are interested in going back, if you came in late. And I'll see you all in class later.